Okay, um, let's start the class. So I hope there are enough spaces. So my name is Russ, and I'm going to be the instructor for this class. The class is basically going to be very similar in flavor to the class that Katrina and I taught last year. Before I get into the specifics of the class, let me just go through logistics with you. So the prerequisites for the class is that you have to have some good knowledge of linear algebra, optimization. You have to be, well versed in machine learning. You have to know a little bit about deep learning and such. So use your own judgment of whether this is a suitable course for you or not. This course is going to be a fairly mathematically intense course. So you will see as we go through the lectures, there's reading material and such. In terms of the grading, we're going to have 3 assignments and the final project. Each assignment is going to be worth 20%. We're not going to have midterms or finals. So it's just 3 assignments and a final project. Halfway through, we're going to have a midway project proposals. So you will basically be handing in your midway project proposals, basically outlining what is it that you want to do. In terms of TAs, collaboration policies, late policy, office hours, and such, everything is going to be announced on Piazza. Okay, so this is your best tool to look at what's going on, because it can dynamically change. Different TAs doing different office hours and such. So look at Piazza, okay? You should all be on Piazza. Let's see. A couple of other things that I want to make a point here is that some of you might be just taking the class for auditing, not necessarily taking the class. The policy is that if you're auditing the class, you don't have to submit your assignments, but you will have to submit your project. And for the project, you're going to get pass-fail grade. Okay? Now, this course is a graduate level course, so you have to understand that. And for the assignments, most of the assignments are going to have questions which will basically have the right answer. So it's a little bit easier to grade. And then there's going to be a coding component. And the coding component is going to be, not as straightforward as, you might think, because it's a deep learning course. You're going to be implementing some of the deep Q networks and such, policy gradient methods and stuff like that, which will require for you to do a little bit, be a little bit more mature. In the past, some students had problems with the homeworks where they look at the homework and it requires some exploration. So typically, your programming homeworks will not have a unique answer. It's like algorithm A is better than algorithm B, right? So you're going to have to use your own judgment, do the experiments, and provide justifications to why one algorithm is working better. A lot of it will depend on initialization, on how you're training these models, and so forth. Okay? So be prepared for that. Now, I'm also going to let you use your own judgment for how you think this course is going and how hard it is. If you think it's too hard for you, you better off drop the course. Just make sure that you are using your own judgment, right? Because it happened to me in the past where a student would come in halfway through the course after the drop deadline and basically say, I have no idea what's going on in the course, but I need to pass, otherwise I can't graduate, right? So make sure you're not in that situation, okay? If you feel that the course is hard, it's okay to drop it. Projects. Oh yes, one other important thing I want to make, and I'm going to be very strict about this. Every student who's taking this course will get 10 days of grace periods, okay? So what does that mean? That basically means that you have 10 days to be late for your homeworks or projects or midway reports, however you're counting it, but it's 10 days cumulative, right? And after that, you're going to be hit with a harsh penalty. So every day you're late, 10% of your grade is going to, be subtracted from your grade. So it's 10% penalty for late days. Okay? So in other words, if you are submitting your second homework assignment, but you have an interview, you have to go to the conference, you have job interviews and whatnot, you can be late, but only up to 10 days. So you can be late for homework 1, homework 2, homework 3, or for your final project, cumulative 10 days. After that, I'm not going to give you any more late days unless you have medical, proof that, things, if you have like medical concerns, or, you have to have a doctor's note basically saying that you couldn't complete your homework on time. Is the question?
Is the 10% cumulative?
No, 10% for your particular home. If you like late.
Every day, like the next day, is it like plus 10% or?
No, it's 10% of your basically like, you're thinking about 100%, one day it's going to be 90%, then it's going to be 80% and so forth, right? So basically, okay, what happened to me last time is that everybody used the 10 days for the first homework, right? And then a lot of people, actually that's true, a lot of people who got an A in class would get B plus or would get A minus, which is a shame because they were late, okay? And that's not good for your GPA and, just generally, like imagine that you're doing all this work, you're doing excellent work, you're getting an A in the class, but because you're late and you didn't time yourself properly, you're going to get A minus or B plus, right? Just because, so please use your time appropriately, okay? And I've had people coming to me and saying, look, I actually have a whole bunch of midterms or assignments due the same day as your second assignment is due. Can you give me 2-day extension, right? So that's why I'm giving you 10 days, but that's cumulative. And after that, I'm going to be pretty strict about your grades, okay? So don't use your late days if you can. Use it only in special circumstances where you have job interviews, you need to travel to the conference and so forth, okay? Okay. And people can also audit the course. So if any of you want to audit the course, you're more than welcome to come, and audit the course. There's also online section. So for the online section, you can watch the lectures online. Okay. If you are watching the lectures online, even if you're in sort of this course, if you decide to just watch the lectures online, that's fine. That's what happened to me last year. I had 300 students in the class, and about 50 were showing up for the actual lectures. But in that case, that's okay. In that case, just make sure that you're keeping up with the course, because people have a tendency to sort of watch lectures online at 2 times the speed or 3 times the speed of the lecture. And then problems come up when you have homeworks, because people are confused as to what the homeworks and how we're doing this and so forth. Okay? So it's up to you. Project. So project is going to be worth 40% of your grade. So it's a pretty important part of this course. And as I'm showing here, the idea of the final project is to give you some experience trying to do some original piece of research. Some of you who are, just starting your master's, it's an experience for you to do some original piece of research. For some of you who are a little bit more senior, sometimes people think about doing research that potentially can be published as a paper. It's your choice. What's expected? It's expected the original idea. You describe clearly, you relate to existing methods, implement, test in some real-world problem. You'll need to write some basic code, run it on the data, make figures. Basically, think of it as writing an 8-page NIPS paper. Okay? Now, I'm not expecting for every single project to become a NIPS paper, but generally that's the goal. Okay? So you're going to have an introduction section, related work section, description of your method, experimental results, and conclusions. Everything has to be fit into 8 pages. Okay? So we're just trying to prevent people from writing like a 50-page description. So it's going to be 8 pages. Make sure you do that. The other thing that you have to do for the homeworks for the projects and for everything is to use LaTeX. Okay? This is a graduate level class. If you don't know how to use LaTeX, please learn now. Please don't submit, your assignments in Microsoft Word. Try learning LaTeX, and it takes a little bit of time. We're not going to be accepting handwrite, even though it's probably much more efficient for you, but it's much more problematic for TAs because sometimes very hard to read like the handwriting of the students. So basically, just make sure that everything you do, you're doing in LaTeX. And this is a graduate level class. I think you should be comfortable with that. Okay. For the projects, you're also welcome to work in the groups of up to 3 people. You can work by yourself, you can work in the groups of 2, or you can work in the groups of 3. Okay? Generally, last year, most people were working in the groups of 3. It just helps a little bit easier to share the resources and the code and so forth. Okay? And as we go through the course, I'll talk a little bit more about the project and what's expected. But in the back of your mind, you should start thinking about generally what your project should be about. Any questions? Yes?
Does it have to be something completely new? Can it be based on something?
No, it can be based on something. It doesn't have to be completely new. Generally, as we go through the course, you'll read some papers, you'll think about some interesting ideas. You can say, well, how about I try this algorithm and this algorithm on this particular problem and see how it performs and such. So that's okay. As long as you have a very coherent write-up, that's the goal. Yes? Yes, so computing resources. Good question. That's always a tough one for this course. So the first homework assignment will not require you to have extensive compute resources. For the second homework, we will need to make use of heavy compute resources. So we are requesting some GPUs from Pittsburgh Supercomputing Center. If that's successful, you'll have access to GPUs. And later on, we're also going to have access to AWS through the credits. Hopefully that will go through. And people who basically will survive the first homework, you will get the credits, AWS credits, to do your second homework. Okay? Right now, there are about 300 students enrolled in the class if I look at both sections. It's a lot. If you have your own GPUs or your own compute resources, that's even better. If you don't, we'll work something out. Again, you'll have access to AWS or Pittsburgh Supercomputing Center, right? So you'll have some resources to do homeworks and work on your projects for this class. Okay? Any other questions? Oh, yes.
What kind of topics have you
Yeah, so for the projects, once we get closer, like after a few lectures, we'll revisit that. And I'll tell you a little bit more about what kind of projects or topics you should be considering, okay? Okay, so let's dive into the class. So the book that we're going to be using for this, yes?
I'm not sure if I missed it coming in. What homeworks? Is it the first two or 3?
So the first homework is individual, okay? Second homework, we'll see. A lot of it is kind of like constraint optimization problem. How many students are in the class versus how many compute resources we have, and we have to massage it a little bit, okay? But the first homework is individual homework. So the first homework is going to be out in 2 weeks of classes. You will have 2 weeks to do the homework, okay? And then the first homework is you're going to turn it in after 2 weeks, and you're going to get the second homework. And you're going to have 2 weeks for the second homework, and so forth. So it's going to the pace is going to get quite extensive for you, so that we have enough time in the last month of the class for you to actually do and focus on your projects. Okay? Okay, so this is the book that we're going to be using, the Sutton Bart's book on reinforcement learning, an introduction. It's available online, so you can go on the website and download the book. You can look on my website. I'm going to be posting lectures, the PDF versions of the lectures, as well as what you should be reading. It's an excellent book. You should look at it. And we're also going to be using a deep learning book by Goodfellow, Benjo, and Coville to basically look at some of the deep learning algorithms there. Okay, we're going to have a few lectures just on deep learning so that we have a little bit of understanding. How many of you have taken a deep learning class before? Okay, some of you, but not all of you. So there's going to be a couple of lectures where we're going to cover basic convolutional networks and stuff like that, because we'll need it for some of our homeworks. Okay? Okay, so what are we going to be covering today? So we're going to look at the agents, actions, rewards. We're going to look at the Markov decision process and look at the value functions and the optimal value functions. Okay? Okay, so the overall agent environment interface, you have the following setting, right? You have an agent takes an action, and the action would affect the environment, and the environment would spit the next state, right? Which then goes back to the action, goes back to the agent. The agent takes an action, it affects the environment, the environment spits the next state. So if you think about the environment, we always have a state of the world. Think of it as maybe just a visual representation of the world, or whatever the state is. You take an action, and sometimes you get the reward. The reward signal is basically telling you something about was that a good action or not. Typically in the reinforcement learning environment, these rewards are going to be very sparse. So once in a while, you get a feedback saying, was that a good action or not? Okay? So it's a sequential process. And rewards are basically specifying what the agent needs to achieve, not how to achieve it. Right? And that's the beauty of reinforcement learning, because it's the simplest and cheapest form of supervision. Right? So let me give you some examples of that. So for example, if you look at a game of backgammon, the state would be configuration of the playing board, like the configuration of these checkers on the board. There's about 10, 20 different states you can consider. The action could be a move, move one piece to a particular location. And the rewards could be just simple as, did you win the game? The reward is +1. Did you lose the game? The reward is -1. Otherwise, the reward is 0. There's no reward signal. So you can imagine this is a very sparse reward signal, right? You're playing the whole game, and only at the very end, the system is telling you, was that a good sequence of actions or was that a bad sequence of actions, right? And if you contrast it with supervised learning, in supervised learning, you can think of it as at every single state, you're actually receiving the reward. Like somebody's telling you, this is the correct action to take. And then you're in a new state, and somebody's telling you, no, this is the correct action to take. This would be supervised learning, right? And so what makes reinforcement learning more difficult is that your signal that you're getting is actually very sparse. And we'll come back to this problem again and again as we start looking at different algorithms. Here's another example. States could be, the road traffic, weather, time of the day, whatever the visual scene you're getting. The actions could be visual glimpses from the mirrors, cameras in front, like where you should be looking and paying attention to. And the rewards could be +1 if it's safe driving, and -1 is you basically receiving honking from surrounding drivers. Okay? So that would be bad. It's just another example. This is an example of something called conservative exploration strategy, which is very difficult to achieve. Is that what we'll see in a lot of reinforcement learning settings? You have a policy and you run the policy and you say, what kind of reward are you getting? Are you getting positive rewards or getting negative rewards? Now imagine that you're trying, as a human, you're trying to learn how to do, what's it called? Spinning, right? It's a very difficult thing to do, right? And humans are very good at it because you can't afford, trying to do this thing millions of times and 99% of the time actually falling, right? So you need to kind of sometimes it's called conservative exploration strategy. You're really very conservative with what you're exploring and how you're exploring. Because if you're doing something wrong, you can hurt yourself, right? Here's another example. States, which is pole angle or angular velocity. Actions could be move left and right. So you're trying to maintain the pole to be stable. And the reward could be 0 while balancing. So you're not getting any reward. And -1 for imbalance. So if you sort of not balancing it, you get negative reward. So in this case, obviously, you can see that over time, you're trying to just maximize your reward. You're trying to, not go too much into the negative, or stay at 0 as much as possible. Right? Here's another interesting examples where the state could be joint configurations of robotic arm. The actions could be torques on the joints that you're executing, right, for the arm. And the reward could be penalizing jerky motions. So you don't want to end up having a jerky motions, and typically it's could be inversely proportional to distance from the target post. You typically have a target post, what that should be. In fact, there's a lot of research in that space. It's actually pretty difficult to to figure out how to grab something. There was a beautiful, it was amazing. There's an interesting competition set up by Amazon where they set up a challenge where they wanted to build robots that can pick things up. You grab something and you put it on, on the shelf. And a bunch of teams competing. It's an extremely difficult task to actually grab something, like even if you know what the shape is, and put it on the shelf. Can you guess what the winning team do? How they succeeded? So the winning team basically said, well, forget about the arm thing. They just created like a suction, and they just like go to the object, they create a suction, it just sucks it into, and so they don't even have to grab it, and then go and they put it on the shelf, right? So they basically avoid the whole problem of grabbing. It's just, so there are always creative solutions. Now the agent should be able to measure its success explicitly, right? In many cases, you need to be able to get the reward. Was it a positive, was it a negative? Because if you don't get the rewards, you basically have no idea, was it good, was it bad? And oftentimes we can't automatically detect whether the task has been achieved. And as we go through the course, we'll look at something that's called reward shaping. How do we create an environment where we provide intermediate rewards to the system, right? Saying, well, this is good and this is bad. Not necessarily going all the way to the completion of the task. Now, limitations. So here's the question. Can you think of a goal-directed behavior problem that cannot be modeled or are not meaningful using the Markov decision process framework? We'll talk about this. And a trial and error reinforcement learning framework. Okay? So there are examples where this is difficult to do. And the whole thing about reinforcement learning is that the agent should have enough chance to try and fail enough times, right? So think about this state space. You want to be able to explore this entire state space and figure out which actions are good, which actions are bad, right? And this is generally impossible if an episode or one particular instance takes too long. For example, your reward could be obtain a great PhD, right? So here it's very difficult to do reinforcement learning, right? Because you can do PhD maybe how many times? Maybe twice in your lifetime? Once? Twice. I've seen people having 2 PhDs. But that's about it, right? So, and generally, this is impossible when safety is in concern, right? So for example, it's very difficult to learn to drive via reinforcement learning in the real world, right? Because you can't build a system and say, okay, well, run this policy. You hit another car and say, well, that's bad. Let's try another one. You hit a pedestrian and say, well, that's also bad. Let's try another one. So generally, this is one of the challenges of reinforcement learning, right? So we'll talk about this as we go through the course. So let's look at the definition of the MDP. And as we go through many lectures, the next 4 or 5 lectures, we'll be coming back to MDP. And something that I encourage you to look at Rich Sutton book, the first few chapters, if you've never seen the Markov decision process, because there are a few things that you need to be familiar with and kind of memorize, almost memorize. So Markov decision process is a tuple. You have state. Right now, we can assume that state is a finite set of states. Later on, we're going to go to the continuous set of states. A is a finite set of actions. Again, actions are now discrete and finite. Later on, we're going to look at continuous actions. T is going to be a state transition probability function. So the state probability transition function basically is telling you what's the probability of the next state given that you're in the current state and you take an action A. Okay? So this typically is a probability distribution. Now, in some cases, if your dynamics is specific, then you can kind of like or deterministic, maybe the next state is just deterministic. Think about like playing an Atari game. Your environment is your environment. You click on the left button, and your state, the next state, is a concrete next state. Like, your tank moves to the right by 1 pixel, right? But in more realistic scenarios, is actually distribution of possible states, right? Because the future could be multimodal. I don't know, what would the example of that be? But generally, if you take a particular action, the next state could be one or could be another, right? And sometimes it's difficult to predict what the next state would be. I'm just keep thinking, like, if you run when you hit somebody, right? What's the probability of the next state? Probability of the next state, the other driver would jump out and just basically go fist fighting with you if you live in certain countries. Or it could be just nothing happens, right? The driver comes out and starts a discussion with you, right? So again, the probability of the next state could be multimodal distribution. That's actually something that we'll talk about later in this class, okay? R is the reward function, right? And we'll look at the definition of what that means, but think of it as an expected reward given you in particular state and you take a particular action, right? So the expected reward, in many cases, the reward would be just one reward, or if it's an expectation, it's, could be distribution of possible rewards. Again, we're working within the probabilistic setting here, but it's expected reward. And gamma here is the discount factor. We'll see later, the discount factor is typically saying that immediate rewards are more important than further rewards or future long rewards. So something that's immediate is more important to me than something that's going to happen later in my episode. Okay, so now we're going to be making an assumption that actions are discrete. Actions can have many different temporal granularities, okay? So let's look at the state. What's the meaning of the state? So the state captures whatever information is available in the agent at time step t about its environment, okay? So the state can include immediate sensations. So think of it as, if you have a robot, the robot has some sensors, cameras, right? So whatever you're visually seeing now would be your state. If you have range sensors, if you have connect or depth, that could all be part of your state. And it could be highly processed sensations or structures built over time from sequence of sensations or memories and so forth. Sometimes people are keeping, cumulative average of everything that they've seen so far, right? So that could mean the state. And a state should summarize past sensations and to retain all essential information. So in other words, throughout the rest of the course, we're going to be making assumption that we have a Markov property, right? So the probability of the reward and the state, given the entire past history of the sequence of states and actions that we were taking and rewards, is just going to be given the probability of whatever reward in the next state, given the current state and the current action, okay? So we're always going to be making a Markov assumption. And we should be able to throw away the history once the state is known. Once we know the state, ST, condition on ST, we don't really care what happened at ST minus 1, ST minus 2, and so forth, okay? Now, an agent can be blamed for missing information that's unknown, but for forgetting relevant information, right? So for example, when you're building models, if some information is missing, there is nothing you can do about it, right? But if you're forgetting some relevant information, or you're not including it as part of your state, then you're not going to have a good system, right? So a lot of work is in the future when we'll look at some applications of deep reinforcement learning. A lot of it comes down to what's the representations you're learning about the state. Are you retaining all the relevant information so that you can achieve the task? So here's an example. What would you expect to be the state information of a vacuum cleaning robot? Right? What do you think the state should be? Could be position, could be amount of dirt. If your vacuum cleaner has camera in it, it's like visual representation of the world. If you have some connect sensor, depth sensors, that could be the representation of the world, right? So everything that you're seeing so far. You can also have, some kind of exponential moving average, perhaps of some of the previous states. And again, that would maintain the Markovian property, because once you have that, you disregard everything else. So, and obviously, how do what the state is going to be very problem dependent, right? Depending on what problem you're trying to solve. So now let's look at the dynamics. How does the state change given the actions of the agent, right? And there are two approaches, and there's a big debate between two different approaches. There is a model-based approach, which basically says the dynamics are known or are estimated. So in other words, you're actually trying to estimate what's the distribution of the next state given your current state and the action, right? Sometimes people also call, think about if you have a robot, let's say you have some camera input, so you have some visual field, you're basically saying, well, if I turn left, right, my action is to turn left, what would my next state look like? So if I turn left, that's what my next state would look like. So the question is, can you actually build a predictive model of what the state would look like? So there are some approaches based on, deep learning, encoding, decoding type of models that try to predict what the next state should be given my current state and the action. We're trying to estimate what the model-based dynamics looks like. In many cases, we might know what the model dynamics is, right? Based on physical constraints and so forth. And the model-free approach, we basically don't know the dynamics of the Markov decision process, right? So we're going to try to estimate the optimal policy without knowing the dynamics. And in practice, the dynamics are going to be unknown. In general, it's very difficult to predict the state of the world. But the state representation should be such that it's easily predictable from the neighboring states. That's one of the assumptions that we're going to be making in terms of generalizability. If you see the state, if you see a similar state, maybe the action that should be taking should be similar in both cases, right? Because the state is not changing that much. Yes?
Would model 3 be the same as learning the transition function?
No, when you're learning the transition function, you're actually trying to learn what the dynamics is. And then you can unroll it into the future and do planning. So you're actually trying to estimate it. Model 3 basically doesn't, you don't really need to estimate the transition probabilities. And we'll look at both approaches. Yeah. Now let's look about rewards. So the return G sub t is the total discounted reward from time step t. That's going to be our definition, right? You're at time step t. You take an action, the environment gives you the next state, and you get the next reward. You take another action, you get another state, you get another reward, and so forth. So G sub t is the total discounted reward that's kind of expressed here, up until infinity or up until the episode is terminated, once you reach your goal state. And the objective of reinforcement learning is to maximize the long-term future reward, right? The goal of reinforcement learning is to maximize this thing, right? And so you want to choose a sequence of actions A sub t, or in general, you want to choose the action at the current time step t, such that you're trying to maximize the sum of all future discounted rewards. And obviously, gamma here is something called discounting factor. That, again, something that the model, it's up to you to set or to design. Generally, I've seen in practice people use the value of 0.9. It's kind of like if you ask, I'm building my deep learning system, what my learning rate should be, the answer is 0.01. Right? That's it. So here it's 0.9. So there are also two types of tasks that we're going to look at. There's episodic tasks that have finite horizon, right? So you go with something and then you stop your question.
Is it always the case that gamma is a constant, or are there cases where some periods of time are valued more?
Yeah, no, gamma doesn't have to be constant. It's up to you to design, maybe in certain cases, but it's something that up to, think of it as a hyperparameter that the model has to specify, right? Because it's really just a trade-off. If I set my gamma to 0, then what it's saying is that I just want to take an action so that my next immediate reward is as high as possible. I don't really care what's going to happen in the future, right? If your gamma is 1, you're really basically saying if this reward is small, but in the future I'm going to get big rewards, then I'm going to take this action, even though initially it might, it's like you guys are going to the grad school, right? You're sacrificing, getting a high-paying jobs and making a lot of money, and you're paying tuition, you're going through that stage in the hopes that in the future you get, much higher-paying jobs, right? And more interesting jobs. So it's exactly how you optimize for your gamma. Yes?
Just a general question on the setup. In this framework, are we assuming that the environment is only representing that can change by itself?
Yeah, so right now we're just going to make a very simplistic assumption. We're not going to make we're going to make an assumption that the environment is stationary. So it doesn't change over time. There are settings when the environment can change, and that's even more challenging, right? Because you are in one environment, you take an action, you get the reward. Now environment changed, and you're in the same state, you take the action, get negative reward, and you basically say, whoa, what's going on? But for this class, we're just going to make an assumption that the environments are static. But obviously in the real world, environments are changing. So you have to take that into account as well, which is even more challenging. So episodic tasks, finite horizon. Continuous tasks, infinite horizon. So you get basically a robot just, never stops, creates new things, it does things. Most of the time, we're going to be working with episodic tasks, just for simplicity. This is just an example of a student MDP. We'll come back to that, but imagine that you basically, each state is your state, right? And you have probability of transitions. Like for example, if you're here, you have 0.5 probability of studying and then reaching the terminal state, which is, that's the terminal state. Or with probability 0.5, you can go to the pub. And after the pub, you can reach this state, or that other state, right? And so forth. And obviously, the more time you spend on Facebook, the more negative rewards you're accumulating, right? So, definition of the policy. That's one term that you will need to kind of be familiar with. That's the most important term. What is the policy? The policy is distribution of actions given the states, right? So if I'm in a particular state, what action should I be taking? And that's typically going to be distribution of possible actions. If you have discrete set of actions, it's going to be distribution, softmax of possible actions to take. So a policy pi defines the behavior of the agent, right? Because it tells you in this particular state, here's the distribution of possible actions. You can either sample it or you can take the most probable one. And the MDP policies depend on the current state, not the history, right? In other words, the policies are stationary. So we're going to be making assumption that AT is sampled from some policy that's going to be fixed throughout the time. This is a stationary policy. Now, in many cases, you can also become fancier and define policies that are non-stationary, that can change over time and such. But for now, we're going to make an assumption that the policies are stationary. Okay? So, how do we solve MDP? Ultimately, we want to find the optimal policy. And there are certain tasks for us to consider. One task is the prediction. So the prediction task is basically saying the following. If I give you the policy, estimate the value function of the states or state action pairs. And we're going to look at that. What does that mean? What's the value of the state? Okay? So this is more of a prediction task. It's basically saying, okay, if I have this policy, can I estimate how good each state is? Right? And that's going to be the prediction task. There's a control task, which is estimate the value function of states and state action pairs for the optimal policy. So this is basically saying that if I had access to the optimal policy, what would the value of the state be? And again, we'll see some examples of that. So, value functions. The value functions are basically measuring the goodness of a particular state. right? Or state action pair. How good is for the agent to be in a particular state or execute a particular action at a particular state? And that depends on the policy. Here's an example. Imagine you have a robot and you're standing in a state, particular state. If I move to the left, I fall off the cliff. Imagine I'm standing on, on the edge of the cliff. If I turn left, I fall off the cliff, right? If I turn right, if I move right, then I'm okay. What do you think the value of the state would be? Is it a good value? Is this, you think that it's a bad value? I mean, imagine you standing on the edge of a cliff. Would that be a good value or a bad value? Bad value. But again, if your policy is random, you flip the coin and you say, probability half I move to the left, probability half I move to the right, then this definitely would be bad value. Because with probability 5, probability 0.5, you fall off the cliff, so you get big negative reward. Actually, your reward is going to be minus infinity, right? You're done. But if your policy is to move to the right, if you're in this particular state and your policy says with probability 1, move to the right, then the value of the state is not so bad, right? Because you move to the right and then you do something and get some positive reward. So a lot of it depends. That's why these value functions are functions of the policy, right? And the optimal value functions measure of the best possible goodness of states or state action pairs under any policy, right? So in other words, whatever policy you have, you want to see like how good the state is. And generally, the state where you're standing next to the cliff, the value of the state is going to be small or negative, right? Now, let's look at the definitions now. What's the value of the state? So the state value function v pi sub s, or I guess v sub pi s. So according to a particular policy, the value of the state of an MDP is the expected return starting from state s and then following policy pi. Okay, that's the value of the state. So it's an expectation of the reward, cumulative reward, if you start a particular state S and you follow policy pi. Now, obviously, your policy pi is a distribution, right? Because given a particular state, you have a probability distribution of different states. So that's why you're taking expectations, right? And that's why if you're standing next to the edge of the cliff, if your policy is random, then the expected value is going to be a very big negative number, right? So that's the definition of the value of the state. And a couple of classes down the road, we'll see how do we evaluate these policies. There are ways of doing something that's called Monte Carlo evaluation. There's something that's called temporal difference learning and so forth. So we'll come to that. The action value function Q, Q sub pi SA, is the expected return starting from state S and taking action A, and then following policy pi. So the two definitions are kind of fairly similar, right? Q values is basically saying if I'm in state S and take action A, right? What's the expected return going forward? The value is basically almost like marginalizing or taking expectation of the possible actions. So this is a little bit more fine-grained definition here, right? The optimal value function, V, is the maximum value function over all policies. And that's what ultimately we want to find out, right? So this is over the maximum value under over all policies. Whatever the policies you could have, this is the maximum one, right? And the optimal action value function, Q, is the maximum action value function over all policies, right? So whatever policies you throw at it, just takes the maximum. This would be your optimal value of the state or optimal action value function, okay? And ultimately, I think in the next class, we're going to look at some ways of trying to estimate what these things are, right? So that's finding the optimal policies, basically. Now, a lot of these definitions are going to be based on Bellman equations, or Bellman expectation equation, which kind of has the following structure. So let's look at it a little more carefully. So the value of the state, its expectation of the return, starting in a particular state, S. This is the definition, right? So RT plus 1 plus discounted and so forth. Well, I can pull this out, right? And I can say it's the next immediate reward plus gamma times GT plus 1, right? And if I push the expectation inside, the correct expectation inside, I'm going to get this expression here. So this expression, if you think about this, and again, you should look at the book, chapter 3 and 4, I believe, that sort of goes through the definitions of these equations. But the value function can be decomposed into two parts, and it's actually very intuitive. It underlies a lot of different RL algorithms. You have an immediate reward, discounted value of the successor state that you end up in. Okay? So think about, in supervised learning, I'm sure many of you look at logistic regression or neural nets or whatever that might be. You have a state, which is the input image, and you predict the class, right? And it's either right or not. You basically say, is there a dog or not a dog, right? This equation is essentially saying the following. It says, what's the value of the state? Well, the value of the state is expected reward. So if my expected reward is good, that's good. Like I take an action, I get big positive reward. That's good, right? Plus the value of the state I end up in, right? So for example, if I'm in a situation where, this is the robot, and imagine I take the action to the left. I go to the left, so and this is the edge of the cliff. But maybe I get big positive reward because, it's fascinating to be at the edge of the cliff, right? So you get big positive reward by going into that state. But now if you start looking at the value of the state might be might be a very big negative number, right? So now you're basically saying, okay, what's my reward versus what's the value of the state I end up in, right? And that underlines a lot of different RL algorithms. Think about when you're driving, you're rushing, you're basically saying, oh, do I cut this guy off? If I cut this guy off, I might go through the traffic light and save myself time. That's positive reward. On the other hand, this guy might hit me from the back, right? And so the state that I end up with might not be so good. And so you're kind of like manipulating yourself, right? Of course, you kind of like look at the car. If the car is kind of old-looking car, there's a teenager behind the car, you basically say, oh, no. Your value of the state now goes up because he's definitely going to hit you, right? If it's a nice car and your car is kind of like so-so, I've observed in Boston, that's the rule in Boston. If you drive in Boston, and whoever gets the first right of the way is the person with, the oldest and smashest car, right? And everybody lets this person go up in front. So you sort of balancing these two things, which intuitively should make sense for you, right? You're balancing how good of a reward you're getting versus how good of a state you end up in. If you get big reward and you end up in a good state, that's good. If you get big negative reward, but you end up in a good state because the future rewards might be big and positive, then it's also a good, the value of state increases, right? So always remember that there are these two factors that are in play. So the state value function can be decomposed into immediate reward plus discounted value of the successor state, as we've seen. The same thing happens for the action value function, right? You have the reward plus the Q function at the next time step. Yes? Yes, these are the expectations. So these expectations, sorry, they should be an expectation with respect to t as well. So when I think about expectation, it's an expectation under the policy with respect to all the unknown variables. Right? So looking inside the expectations, the way you can think about this is what's the exact definition of the value of the state? Well, this is an expectation with respect to pi, right? You're getting the reward plus gamma. And this is an expectation, this is definition, once you push the expectation inside, of your transition times the value of the state, right? That's just the definition of writing out what is the value of the state. Now, in many cases, maybe if this is in some kind of deterministic function, if you're in one state, you take an action, you end up just in another state, there is no uncertainty, then this would be just, the indicative function of the next state. If there is some uncertainty in the world of what the next state might be, you have to take this into account, right? And so that's why you have the value of the state is just an expectation with respect to these two things. In practice, generally, do you know this? That's a hard question to ask. In many cases, you don't know what that is. So you either have to estimate it, or there are ways of model-free reinforcement learning that kind of avoid this thing altogether, or modeling that particular thing. Same thing for the Q function, action value, right? The Q function, if you're in a particular state, you take an action. Once you take an action, you get the particular reward. Again, it could be positive, negative, it could be 0. And then here you're taking expectation with respect to the states, right? And here you have an expectation with respect to the actions. Obviously, you can write. Okay? And again, if your transition is deterministic, right, then it's just the indicator of the next state. And this is just the expectation by marginalizing of possible actions. So here's the relationship between state and state action value function, right? What's the definition of the value function? Well, it's actually the relationship is your Q function of particular state, taking particular action, just taking expectation with respect to the policy. That's the value of the state, right? So if you end up in a state where you have two actions, right? One action, one value is good, the other one is bad, then the overall value of the state would be, the average of the two, weighted according to the policy, right? So that's just the definition of value of the state and the Q function. So sometimes people prefer to work with the Q function. Sometimes you'll see examples, people are looking at the value of the states, either with this or with this. But once you have the policy, you can find one from another. This is just a little bit more definition, a few equations, what that means. This is definition of the value of the state. This is definition of the Q function. And this is just the write-up of the relationship. Once you plug this in here, you get this particular representation. So in other words, if you have the value of the state, somehow, if you have access to that, you can compute the Q function on the policy pi. Right now, we assume that the policy is given to us, right? And we're just kind of like figuring out what's the value of the state, what's the Q function of a state and an action. Obviously, in the future, you really want to figure out what this thing is, right? What's the optimal policy, right? And later on, we'll look at the algorithms that basically kind of like do EM-like steps where you first, given a fixed policy, you try to estimate the value of the state in your Q function, and then given the value of the state in your Q function, you're trying to re-estimate the policy. Try to take a policy that's a little bit better, right? And so forth. So we'll look at some of these examples. So for example, here's the value function for the student MDP. The way you compute the value of the function being in this state is given here, right? It's probability 5, your reward is, with probability 5, your reward is 10 and you go to the terminal state. With probability 5, you get the reward 1, plus with probability 0.2, you end up in the state minus 1.3 and so forth, right? So based on this calculation, you can basically say, and these are policies that are given to you, right? This is the policy saying once you're in this state, probability 0.2, you go to this state, probability 0.4, you go to this state, probability 4, you go to that state. Okay? This is just an example for you to kind of look at this basic MDP. And I think for your first homework, you'll play with MDPs and do some manipulations and calculations. Now, the optimal state value function is the maximum value function of all policies. We've seen that. And the optimal action value function is the maximum value. So the optimal equations for the state value function is basically given here. So what's the optimal value? Instead of taking expectation, which is the value of the state, you can actually take the maximum, the actions. So you're basically taking the action that gives you the maximum immediate reward, plus you take an expectation with respect to the optimal one, right? And same thing happens for the Q function. So the optimal Q function, you have the reward, and then you're taking the maximum action. So generally speaking, the optimal policy actually, I believe in many cases, there are some exceptions, but in many cases, the optimal policy is going to be deterministic. Like once you're in one particular state, there is one action to take, right? Sometimes you need to diversify. Later on, we'll see at some of the stochastic when stochastic policies are optimal, but in many cases, deterministic policies are optimal, right? Imagine you have a robot, you're in a particular state. In many cases, there's going to be an optimal action, like turn left or turn right or move forward, right? So that's taking the maximum. So here's an interesting thing. Here's the optimal value function for the student MDP. And the optimal value function here is 10, right? Because you always want to take this action. That's the maximum. You can't do more than that. The optimal for this state is 8. Surprising that the optimal function for, the upper state is positive. I guess because you really want to, like, as soon as you're in this state, you really want to quit, right? That's the optimal action to do, right? And this is also the optimal value function for state action pairs. And this is just basically is telling you that the reason why it's 10 is because your Q function is going to have value, the optimal Q value function is going to have a value of 10 because there's only one action to take, the optimal action, right? So there are two things to keep in mind. If I give you the policy, what's the distribution of the actions given the state, you can compute the value of a state and you can compute the action value function. But finding the optimal value function and the optimal action value function is different, right? This is where you're taking the maximum. So there is no kind of policies involved. Once you have Q values, you always find just taking the maximum action that gives you the maximum Q value or maximal value of the state. And also the optimal value functions are recursively related by the Bellman optimality equations. And it's kind of, here's the definition. The optimal value of the state, instead of taking the average or taking expectation with respect to the policy, it's just taking the maximum. Same thing for the Q function. Okay? So we're sort of like going through a lot of definitions right now, but a lot of these definitions are very simple. So if you haven't seen this before, I would encourage you to go over them a little bit, spend a little bit more time on them, look at the book. These are fairly basic, very, very basic concepts that we're going to be building upon in the next lecture, in fact, in the next few lectures. So optimal policy, we can define a partial ordering of the policies, right? And we can say that pi is greater than pi prime if the value of the state is greater than the value of the state, for policy pi compared to policy pi prime for all states. Now, right now we're working in a discrete domain, right? So we have a finite number of states. So if that happens, then we can have a partial ordering on the policies. And the theorem basically saying for AMDP, there exists an optimal policy pi star that's better or equal to all other policies. Okay? And the optimal policies achieve the optimal value function, and all optimal policies achieve the optimal action value function. Okay? So that is the case. And now, an optimal policy can also be found from just the optimal value. Like if you have the values of the states, the optimal values of the states. And if you actually have the model dynamics, so you can just do one step look ahead and basically acting greedily with respect to the optimal value of the state. Right? So for example, here's the optimal policy. The optimal policy is going to be take this action if A is argmax of all actions of the optimal Q function, which is essentially telling you the following. It's telling you that if you find the optimal Q function or value function, then you can recover the optimal policy from it, right? And the optimal policy is actually very simple. It's basically saying, look at your Q function, look at the best action that maximizes the Q function, and that's your policy. Take this action. And zero otherwise. And then there is always the deterministic optimal policy for any MDP. So if we know the optimal Q function, then we immediately know the optimal policy, right? So in reinforcement learning, we'll see throughout the course, there are a whole bunch of algorithms that try to estimate this thing, right? So for example, if you're familiar with deep Q networks, the Q networks that are playing Atari games, they try to estimate this quantity here. There are also other types of methods that try to estimate policy directly. They try to see, how can I find this thing here without going through here, right? And they're all kind of related, and you have different flavors of methods trying to estimate things different. So policy gradient methods are trying to directly estimate what this thing is. And we'll talk about these different algorithms. Any questions? Yes?
This is also assuming that in your Markov transition system, every path is finite, right?
Yes, that's right. And so for the MDP, if you want to go into a little bit more details, you have to ensure that according to your Markov transition operator, you should be, any state is reachable from any other state and so forth. So there are certain conditions on ergodicity and stuff like that. But for now, we're just working in a finite domain, and the transition probabilities are always some probability of reaching any other state, right? So finding the optimal policy by solving the Bellman optimality equation, we need to do the following, right? We need to know the following. We need to know, or we need to have accurate knowledge of the environment dynamics. We need to know what the transition probabilities are. We need to have enough space and time to do the computation. Obviously, if I only have 1,000 states and maybe like 5 actions per state, then it's okay. But in many cases, like I think Katrina was mentioning last time, in the case of Go, for example, the state space is humongous. It's like 2 to the, I can't remember, like 2 to the 500 or something like that, or 10 to the 500. It's basically exponentially large, right? So what do you do here? And you also need the Markovian property. And the Markovian property might not be, in the real world, that might, your real world dynamics might violate the Markovian assumption. How much space and time do we need? Well, we polynomial in number of states, tabular methods. I think we're going to be quadratic or cubic in the number of states, which is really bad. But the number of states is almost huge. So the exhaustive sweeps through the state space is not possible. Okay? So we're going to look at some examples through this course, and this is where deep learning kind of comes over and tries to basically say, well, we're going to have something called function approximation. And the idea is that even if you have exponential number of states, if I take a state and little states around it are kind of similar, so I'm expecting to take similar optimal actions around it, right? So we'll look at some examples of that. And obviously, we usually have to settle for approximations. We're going to look at approximate dynamic programming. In fact, we're going to look at dynamic programming in the next class, just to give us some idea of how we can learn these policies. But approximate dynamic programming was introduced by Pertsekas and Tsitskilis with the use of artificial neural networks. And so this is where we will later on look in the class of how we can use neural nets to do approximations that will allow us to deal with the exponential state space. And this is effective. It's a fairly effective mitigation strategy where you're dealing with the curse of dimensionality by replacing memorization, by basically a mapping, a nonlinear mapping function, nonlinear approximation function. So we'll look at some examples of that. In fact, in the last few years, the field of deep reinforcement learning kind of exploded. And the reason why is precisely because these neural network methods allowed us to kind of start working in more realistic environments, right? Taking cameras inputs or depth inputs and actually being able to build something that does a reasonable job, Before that, this problem of exponential state space, or this huge state space, was always a problem. So when I was in grad school, reinforcement learning was always this cool field, and you have tons of theoretical work. I can prove all kinds of stuff, but it kind of never worked. You know, it's like, well, so people didn't really pay attention to it. But now, with the success of a few examples in the past few years, the field is actually recharging itself. And it's surprising because a lot of different algorithms, a lot of different concepts and such are pretty old. Like people have been developing these ideas from 50s, basically. So the algorithms and everything kind of remain the same. And we'll look at some of those. So our RL methods, reinforcement learning methods, we're going to be approximating Bellman optimality equations. We're going to be balancing reward accumulation and system identification, so sort of like model learning. How much do we want to learn about the transitions in case of unknown dynamics? And sometimes, in many cases, when we look at online reinforcement learning, sometimes it's possible for us to approximate the optimal policies by looking at more frequently encountered states. So this is something that we're going to look at later on. There's something called prioritized replay that essentially tries to explore strategies or tries to explore states that are more informative or more frequently visited, right? So far, we've looked at MDPs, we've looked at the value functions and optimal value functions, we looked at the Bellman equations, but we also made an assumption that finite MDP dynamics is known. We know what the dynamics is. And this is generally not true when you start building realistic environments, right? In simulation world, you know exactly what the dynamics is. In the real world, sometimes it's hard, unless you have but you can put some prior knowledge also, right? Because we're operating in the physical world, so sometimes we know what the dynamics should be. Okay, so next class, we're going to look at ways of, at least I'll give you some intuitions about how we can find the optimal policies. And then later, in the next classes, we're going to start jumping into more advanced techniques for evaluating policies or learning policies.